up to 64. We'll start with some questions. If anybody's got questions about this stuff. Mackenzie.
Yeah. Can you do number 48?
Yeah. What you want me to? All right. So 48, it says to do this by rationalizing the denominator. Okay. Well, easy enough. So FOIL that out. What did I say? Get 2 minus 3i plus 2i root 3 and minus 3 root 3i squared all over 1 plus 3. So far, so good, Mac? Okay. So in the numerator, I'm going to combine like terms. I know I squared is just like a -1, so my a term is 2 plus root 3, and the denominator is 4. And my b term is the i's. So I got a -3 plus 2 root 3 over 4. And I'll stick the I on the outside there. So it's cool, right, that we have this weird looking thing. This is just an irrational, these are just irrational numbers. They're still just one number though, right? I know it looks like it's a bunch of things. But like this whole thing is my A. And then this whole thing is my B. And there's my I. So it's still standard form. Exact standard form, excuse me. Does that make sense, Mackenzie?
Yeah.
You're trying to do too much, weren't you? Sorting it out. Yeah. It's just one of those things. It's like, why I should be able to add these things? It's like, no, man, you can't. One's rational, one's irrational. If you want to get an exact answer, you best not add them. You know? Amy, did you have a hand?
Yeah, so with FOIL it, you just FOILed the like Z1 and Z2, correct?
Yeah, I just did.
Okay.
I did this times this, and I did, this times that, then I did, this times this one, and then I did that times that one. Just like foiling like we foil it, Foilerooskies. Who's next?
Oh,
Neeks.
Can you do 23?
Yeah, man. Sorry, Paul.
Okay.
It's not intentional. Just people keep raising their hands before you do. 23. Okay. So if I want to do the R, that's going to be -9 root 3 squared plus -9 squared, all square rooted. So 9 squared is 81 times 3 is 243. And then 9 squared is 81, so that gives me square root 324. Is that a perfect square?
So,
Maybe.
it should be.
Let me look at it. Yeah, it definitely is.
It's 9 times 4. So.
Yep.
Wow, Paul.
Somebody brought their A game today.
No.
Paul's always been good.
And then if I draw my picture, there's my guy right down there. There's theta. This is 180. Uh-oh. Oh, let's call it pi since the directions ask for the angle in radians. So that's going to be pi plus alpha, which is the tan inverse of the imaginary part over the real part, but I really mean absolute valued. And this I recognize as one of those unit circle angles, I'm going to do this in degrees just so I can see it a little bit easier. So Nico, I'm just doing the absolute value part in my head and then reducing the fraction just so it's a less hassle to type in the calculator. So that's 30 degrees. So that's the same thing as pi over 6. So pi plus pi over 6 is 7 pi over 6. So my answer then is 18 cosine 7 pi over 6 plus I sine 7 pi over 6. Yeah, no problem. And if you're not sure if something's a unit circle angle, just, like do it in degrees. And then you're like, oh, yep, 30, 60, 90, or 45 multiple. Sure, unit circle angle. Paul.
Number 14.
Okay. So this one's, I'm just going to think about by looking at the graph. So negative 4i is there, right?
Yep.
The distance from the origin is just 4 units. And then this angle's my theta. That's 3 pi over 2. So I just have 4 times cosine 3 pi over 2 plus I sine 3 pi over 2. Done. Cool?
Yep.
So if there's just one component, it's like all you have to do is look at the picture, no arithmetic is necessary.
Okay. Now, when it's in, so like for something like the one we just did, where you have r equals square root of 9, when you have something like that, if it's in the first or fourth quadrant, are you still just adding or subtracting pi?
It's the same rules that we used to solve for angles earlier.
Okay.
So like, since my most recent axis I passed was the horizontal, I'm going to be adding.
Right.
Or on, where was it? I don't know. Some other one, maybe it would be if the most recent axis you passed is the vertical, then you're subtracting.
Okay.
So if you're in the fourth quadrant, you're subtracting.
Gotcha. Is it always adding or subtracting just a pi?
No, sometimes it's 2 pi or whatever.
Right. So like if it was in the fourth quadrant, it would be
2 pi minus alpha.
okay. If it was in the first quadrant, it would be
0 plus alpha.
Oh, okay.
Because the last thing you passed was 0. And
Okay.
Others.
Could you do another dividing one? Real quick?
I don't think we did a dividing one. Oh, I guess that was the rationalized. Which one?
Right. I don't know.
They're all the same, man.
I know. I just want another one.
Okay.
That's why I don't really care which one. So, 47.
Yeah. I mean, sure. Paul, do you mind if we divide it with trigonometric form?
It's fine.
Okay. So since it's in trigonometric form, that's super easy. I'm just going to do 6 divided by 3/4. And I remember to add fractions is the same thing as multiplying by a reciprocal. So that's 8. Emma, you could. And then we'll just subtract the thetas. So negative 8 pi over 3. Hi, thank you. Evan, you got a cup. So I have this minus pi over 2. To do that, I need to have a common denominator. Obviously, that common denominator would be 6. So that's negative 16 pi over 6 minus 3 pi over 6, giving me negative 19 pi over 6. So I put it together, I have 8 times cosine negative 19 pi over 6 plus I sine negative 19 pi over 6.
Did you just subtract the two thetas?
Yup.
Okay. So all you're doing is dividing the first two.
Dividing the r's and subtracting the thetas? Yep.
And it's the same thing for the one up there.
Nope. because this was in trigonometric form. The formula is different. Emma.
So do you not have to add 3 pi to make it positive? It can stay negative?
Sure. I mean, I guess it depends on what the directions say. It just says exact in trigonometric form.
Right.
So it doesn't tell you what theta needs to be between 0 and 2 pi or something. So I'm not going to mess with it. You could if you wanted to. Wouldn't make it wrong. But you don't need to.
You just do number 47.
Sure. 1 minus I over square root 3 plus I. Multiply by the conjugate. FOIL the numerator. And so if I do that, I have negative 1 plus root 3 over 4. That's all the stuff without the i's in it. And then I have negative 1 minus root 3 over 4 I. All the stuff with the i's in it. That's it. Anybody else? Amy?
Could you do number 56, please?
So we're just multiplying these. So multiply them together. So 6 times 3/4 is 9 over 2. And we're going to add the theta, so negative 8 pi over 3 plus a half. Make a common denominator. Obviously, that common denominator is 6. Oops. That gives me negative 13 pi over 6. So I have 9 over 2 times cosine negative 13 pi over 6 plus I sine negative 13 pi over 6. Is that cool, Amers? Yeah, no problem, a dude. Isn't the trigonometric form lovely, though, to do these computations? Like, all you're doing is just, like, adding and multiplying stuff. Woo! Mental mathing it up. Don't even have to get my calculator all fired up to do any of these. That's what I'm talking about. I mean, obviously, you could use your calculator. It would be fun. Yes, Amy.
Okay, so back to 23 with the graph. So
23.
you just took that original equation, like the negative 9 square root of 3 minus 9i, and you put that on track, correct?
Yeah.
Okay.
And I don't even really care where it's at. It just needs to be in the third quadrant. Because I have, like, the real component is negative and the imaginary component is negative.
So then just depending on which quadrant it is, you know, like,
Whether I'm going to be adding or subtracting.
okay.
And then what I'm adding or subtracting to. Yeah.
So it's just a negative and positive signs, right?
Yeah. That's all I really care about. Yeah, man. It's all just about the negatives and the positives. All right, last chance. All righty, here we go. Last section. Yes. Yes. All right. So let's talk about powers first. So let's say we have some complex number in the trigonometric form. If I want to do z squared, that's the same thing as z times z, right? How do I do z times z? I multiply the r's together and then add my thetas together. Okay, just using our formula from last chapter, right, or section. Everybody cool with what I did there? All right. If I wanted z cubed, well, I'm going to think about that as just z times z squared. So I'm going to multiply r and then r squared together. And then I'm going to add theta and 2 theta together. And hopefully at this point, who's seeing a pattern? Okay, so z to the n should be then equal to?
Z times z to the n minus 1.
R to the?
R to the n
Times cosine of
n theta
plus I sine?
n theta.
Yes, sir. This guy has a name. It's called de Moivre's theorem. He was a French mathematician. He invented that.
Awesome.
Or discovered it, depending on your philosophy of whether you think mathematics is invented or discovered.
How do you start discovering that? That's
You just start, you're trying to find out like rules for how stuff works. Yeah, it's awesome, isn't it?
yeah. What's the rule that we don't have yet?
Oh, this is an interesting question. Let's waste a bunch of time. So was a prominent mathematician named David Hilbert, and he made a list of a bunch of problems that were well, at the time were unsolved, and he wanted to this would be a something to focus mathematics research for the future. So he did this in, I don't know, in the 1800s or something, or early 1900s. 1900, there you go. So for the 20th century, he came up with 100 problems.
Okay.
So here's a list of the 100 problems.
Some of us don't solve that.
Some of the ones in red are unsolved.
Okay.
Some of them in yellow are partially solved, and the ones in green are completed.
How do you partially solve?
So you have some of it, but not all of it. You've done some cases, but not all cases.
Oh, I see. Generally applies to things like how would I go?
Yeah, these are considered open questions in mathematics. One of the most important ones is P equal to NP.
Okay.
So P is the set of problems that can be solved with a polynomial time algorithm, and NP is the set of problems where it's impossible to solve with a polynomial time algorithm. Yet to be proven that those two things are actually distinct. Yeah. And if they turn out to be the same, ooh, buddy, that's going to shake up the world. Because most of your cryptography, the data security for your email and stuff is built around these problems that can't be solved in polynomial time. And if they all of a sudden can be, boy, that's a whole data revolution there. Mathematicians are pretty sure they're not the same, but like, we don't know. Nobody's proved it yet.
50-50.
It's not 50-50. It's,
Until someone proves it.
yes, until somebody proves it. It's technically 50-50, sure. Although we're mathematics community's pretty sure they're not the same, but we don't know. All right. So let's do an example here.
That's kind of funny. Well, how safe is your dad? Pretty sure.
Yeah.
That's
Well,
awesome.
and if you read any of those things, they were like read like gobbledygook, probably most of you, because it's using vocabulary none of you guys have. So
Right.
even a lot of those things are things I'm not even really sure what that is. So anyways, here's an example. Let's do it. Use de Moivre's theorem. What do we got here?
5 to the 5th, parentheses, cosine 5 times 14, and then plus I sine 5 times 14.
You got it, dude. So 5 to the 5th is what? 1025? No,
Oh, no.
3125. Right? Somebody do it. Amy, you got your calculator in your hand. 5 to the 5th. Help me out.
3,125.
Woof! Look at that. Mr. Kulik's a ninja. He didn't really do that in his head. He did this problem already earlier today, so he just remembered it. It looks really impressive, though, when he's like, what, it's got to be that? And you're like, wait, how did you just do that? I didn't really do it. I just remembered. So there's that, right? If you wanted this answer in standard form, how would you do that? Perfect, yeah. You just do 3,125 times cosine 70, that's your A. And then 3,125 times sine 70, that's your B. In your calculator it goes. Nothing sneaky. Everybody cool with that? All right. So if we're talking about roots then, so if the nth root of x is equal to x to what power?
N.
1 over n.
Oh, yeah, yeah.
So if I take then the nth root of some, let's give us a z here. And I want the nth root of z then. That's going to be that, right? Look, it's an exponent. Can I just use de Moivre's theorem on it? So it should just be that, right? And I'm done?
Yeah.
Not quite. Yeah. What am I missing?
Because r is multiplied to everything, so the square root of r would have to be the square root of everything. Would you have to solve for cosine first and then square root of it? I don't know.
Just missing coterminal angles. So there's more than just this answer. This answer is correct, but there's more. So what are we missing then? I'm going to write that as the nth root of r now instead of r to the 1 over n because it is a little bit more standard.
Oh, yeah, that's right.
Or if you prefer to write things in radians, you could do it this in radians, right? We just changed the 360s to pi k's, or 2 pi's. 360 to 2 pi. Okay, so let's do an example, right? Yeah, man. Sure. Let's find the cube root of 3 minus 2i. What's the first thing I'm going to want to do? Anybody with an idea? Should be an easy first step. Yes, Mackenzie says get it into trigonometric form because de Moivre's theorem needs to be in trigonometric form for us to use it. Oh, okay, well, easy enough. So square root 13. There's 3 negative 2. So there's my theta. Let's do this in degrees. I think everybody likes degrees better, right? I'm doing the absolute value in my head rather than on my calculator. So 326.31-ish. There. Into trigonometric form. Everybody happy with how we did that? Okay. So now we want the cube root of z. So what did I get? So I do the cube root of the square root of 13. And then what? Cosine 326.31 plus 360k over 3 plus I sine 326.31 plus 360k over 3.
What does square rooting a square root do?
What do you mean? I'm cube rooting a square root. Well, what's the formula?
Oh.
The nth root of r.
Oh, okay. And then square root of
R is the square root of 13.
I see.
Okay, so let's simplify that down. What is the cube root of the square root of 13?
Would it just be fourth root? Or no.
Why?
Because square root is just 2, is like a 2 root. 2 times 3. So
Square root is 1 over, is the exponent 1/2.
2,
Cube root is exponent 1/3. Exponent of an exponent, you multiply. 1/2 times 1/3 is 1/6. 13, the 1/6 is just 13, 6th root of 13. Okay? So when k equals 0, I just have bless you, sneezy. You're welcome, Mr. Kulik. Manners are important. All right, so this is when k is equal to 0. Bless you! You're welcome. So this one, when k is equal to 1, I add those, so I'm going to have 686. Everybody's okay there with what I'm doing? And then if k is equal to 2, that's going to be 720 plus this. Just worth pointing out, 326.31 divided by 3 is 108. 686.31 divided by 3 is 228. And change. I know there's change there, guys. Let's not freak out. And I take the last one divided by 3. I get 348.77. What would happen if I did another one? I would get 468.77. And why don't I care about that? It's coterminal to the first angle. That's why you're only getting you're getting exactly 3 answers, because if you tried to generate more than those 3 answers, you're just getting the same thing that you already have down there. So again, the index of your radical will tell you how many answers you're going to get. If you just keep generating answers until you get a repeat, you don't even need to remember that's how many answers you need. And notice here in the formula we write where k equals 0, 1, 2, all the way up to n minus 1. As long as you pick like n consecutive values, you could start at 10 and then do 10, 11, 12, all the way up to 10 plus n.
Right.
And it's fine.
Okay.
You know, like, it doesn't really matter.
Yeah.
They'll be in a weird order from everybody else, but as long as you like keep going till you get a repeat.
Right.
Like if you forget how many you need,
Right.
it's no big deal. Let's do a sneaky one.
No, not sneaky.
Yeah, everybody likes the sneaky ones. Well, that's why we want to see them now, so it'll be less sneaky come test time. What's the 4th root of 16?
That is 2, right?
Incomplete answer. How many answers should we have?
4.
4. Let's see how. So if I take 16, the r there is 16, and the theta there is 0, right? Because we're just right there. Everybody agree?
Yeah.
So my z is 16 times cosine 0 plus I sine 0. So the 4th root of z is going to be the 4th root of 16 times cosine of 0 plus 360k all over 4 plus I sine 0 plus 360k over 4. Fourth root of 16 is indeed 2. When k equals 0, I'm just going to have cosine of 0 plus I sine of 0. Cosine of 0 is 1. Sine of 0 is 0. So 2 times 1 is just 2. When k is equal to 1, I'm going to have 360 over 4, so 90 degrees. Cosine of 90 is 0. Sine of 90 is 1. So 2 times 1i is 2i. When k is equal to 2, I have 720 divided by 4, which is 180. Cosine of 180 is negative 1. Sine of 180 is 0, so this just becomes negative 2. And if I do then 3 times that is 1080. 1080 divided by 4 is 270. Sine of, or cosine 270 is 0. I sine 270 is negative I. 2 times negative I is negative 2i. So those are our standard form answers, right? These would have been our trigonometric form answers, depending on what the directions we're asking for.
And so K4 would be the same thing as K0? Just
Yes. Yes, you would have gotten cosine 360, sine 360, which is the same as 0. Very good. So this wasn't too bad, right? This is the hardest thing we do, is really this, which isn't even that bad, right? But here, you want to hear the bad part?
What's the rest of it?
So you guys now have done enough to finish. So that's a lot of numbers there. Good news is, after this, we're going to do the homework quiz and get that done. The homework quiz is covering just sections 1 and 2. Yeah, we're going to do that right now. I know, right? Yes. Evan? That's fine. Yeah, pass that forward and hand it to me here. That's cool. Yeah, it's okay. It's okay. Reasonable requests. Hi. Yeah. And those of you that said you need to borrow a calculator, I've already forgotten who the other person was. When I come back to my desk, just come running up after me and I will hand you a calculator.
Oh, someone should definitely just run and like already has one. That would be amazing.
I like how you actually ran.
Yeah.
That was quite literal. Very
It
good.
was, yeah.
Thank you.
You're welcome. Oh, I better stop my recording. While you guys are doing this, I want to say just a couple words.